10:42 p.m., January 16th, 1943. Martha Reynolds crouched in the No. 3 cargo hold of the SS Schenectady, her welding hood pulled down, her torch hissing against cold steel. The temperature outside had dropped to 22 degrees Fahrenheit. The Willamette River water lapped at 40 degrees against the hull. Martha didn't know those numbers. She only knew her fingers were numb despite the heavy gloves, and her weld looked perfect. 23 years old, former seamstress from Spokane, 6 weeks of welding training, now working the graveyard shift at Kaiser's Swan Shipyard in Portland, Oregon. The Schenectady was the first two-tanker completed at the new yard, 523 feet long, designed to carry 7.5 million gallons of fuel oil. Martha had welded deck plates on this ship for 3 weeks, every seam tight, every bead clean. She took pride in her work. The Schenectady had just finished sea trials that afternoon, everything perfect. The ship would deploy to the Pacific in days, fueling the carrier task forces hunting Japanese submarines across 10,000 miles of ocean. Martha's welds would hold fuel that powered the war. Her work mattered. She knew it. Everyone at Swan Island knew it. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. At 10:42, Martha heard a sound like the earth splitting open. A crack so loud it carried across the Willamette River, echoing through southeast Portland a mile away. She dropped her torch, pulled off her hood. The deck beneath her feet was moving, tilting upward. The hull around her groaned with a sound no ship should ever make, metal tearing, rivets popping. The entire center section of the Schenectady was rising out of the water, while both ends sank toward the riverbed. Martha scrambled up the ladder, burst through the hatch onto the main deck. What she saw made no sense. The ship had broken completely in half just aft of the superstructure. The crack ran from the deck down both port and starboard sides all the way to the keel. Only the bottom plates held the two halves together, creating a massive V with the ship's midsection pointing skyward and the bow and stern disappearing into black water. Graveyard shift workers were running toward the fitting dock from every direction. Someone shouted orders. Someone else called for the yard supervisor. Martha stood frozen, staring at the impossible geometry of a 16,000-ton tanker that had folded like paper. Her welds hadn't failed. The entire steel structure had fractured spontaneously, while the ship sat motionless at the dock. The FBI arrived within the hour. Sabotage was the immediate assumption. German agents. Fifth columnists. Someone had deliberately destroyed America's newest tanker on the night before it would enter service. Agents interviewed every worker on the graveyard shift. They examined every weld in the fracture zone. They searched personnel files for suspicious backgrounds. They found nothing. No evidence of tampering. No signs of explosive charges. No indication of deliberate damage. The investigation lasted 3 weeks. Coast Guard engineers inspected the welds under magnification. They found some minor flaws, typical of rapid wartime production, but nothing that explained catastrophic failure. The welds themselves were sound. The fractures had propagated straight through the steel plate, not along the welded seams. Whatever had broken the Schenectady, it wasn't Martha Reynolds's welding. But Martha didn't know that. Neither did the thousands of other women welding Liberty ships and 2 tankers at 18 shipyards across America. What they knew was that ships were breaking. 3 Liberty ships had split completely in half at sea. The SS John P. Gaines broke apart in the Aleutians in November 1943. Only the stern section made it to shore. 10 men died. The SS SO Manhattan fractured while entering New York Harbor in March 1943. The SS Poneganyset split while in convoy in the North Atlantic. Newspapers reported the failures. Investigators blamed inexperienced welders. The narrative was simple and convenient. Women with 6 weeks of training were building warships using a technique that required years of apprenticeship. Of course, the ships were failing. The fault lay with the welders. Specifically, with the women welders who had replaced skilled male workers now fighting overseas. Martha Reynolds quit her job at Swan Island in February 1943. She wasn't fired, wasn't accused of anything specific, but she couldn't stand at her welding station without hearing that sound, that impossible crack echoing across the river. She moved back to Spokane, went back to sewing, told people she'd worked in a factory during the war, never mentioned the Schenectady. The problem wasn't Martha. The problem was that in January 1943, nobody in America understood fracture mechanics. Nobody knew that steel had a ductile to brittle transition temperature. Nobody realized that the cold winter night, combined with specific steel chemistry, could transform normally tough, mild steel into something as fragile as glass. The science didn't exist yet to explain what happened to the Schenectady. It would take a British metallurgist named Constance Tipper 5 years of research to figure it out. But that January night in 1943, all anyone knew was that America's newest tanker had broken in half while sitting peacefully at the dock, and thousands of other welded ships were crossing the North Atlantic, carrying the supplies that determined whether Britain would survive or fall. The Liberty ship program had started as an emergency measure. In May 1941, German U-boats were sinking British merchant ships faster than British, and shipyards could replace them. The math was stark. Britain imported 26 million tons of food, fuel, and raw materials annually. U-boats were sinking ships carrying those supplies at a rate of more than 3 times Britain's construction capacity. Unless something changed drastically, Britain would run out of food and fuel within months. The island nation would be forced to negotiate surrender. Nazi Germany would control Europe. The war would be lost. The British had a design. A simple, cheap cargo ship based on a 1939 British freighter design, 441 feet long, 57 feet wide, single-screw propulsion, triple expansion steam engine, designed to carry 10,000 long tons of cargo. Nothing elegant, nothing fast, just a basic tramp steamer that could be built quickly and cheaply using widely available materials. The British called them ocean-class ships. President Franklin Roosevelt called them Liberty ships, vessels that would bring liberty back to Europe. The American version incorporated one crucial modification. Instead of riveting the hull plates together using traditional shipbuilding methods that required highly skilled riveters working for months, American shipyards would weld the plates. Electric arc welding, melting the steel at the seams until it fused into continuous structure. The technique was faster, cheaper, required less skilled labor. Most importantly, welding saved steel by eliminating the need for overlapping plates. In a war where steel production limited everything from tanks to aircraft to ammunition, saving 400 tons of steel per ship mattered enormously. Welding also allowed for prefabrication. Components could be manufactured in factories hundreds of miles from the ocean, shipped by rail to coastal shipyards, and welded together on the ways. This modular construction technique transformed shipbuilding from a craft into an assembly line. A Liberty ship contained approximately 250,000 individual parts weighing 14 million pounds. Coordinating that complexity required new methods, new thinking, new approaches to an industry that hadn't fundamentally changed in centuries. Enter Henry Kaiser, industrialist, dam builder, man who had never constructed a ship before 1940. Kaiser had made his fortune in massive construction projects: Hoover Dam, Bonneville Dam, Grand Coulee Dam, the San Francisco-Oakland Bay Bridge, projects that required moving millions of tons of concrete and steel, coordinating thousands of workers, meeting impossible deadlines. When the Maritime Commission needed someone to build hundreds of cargo ships immediately, Kaiser understood the challenge wasn't naval architecture. It was industrial logistics. Kaiser established 7 shipyards, 4 in Richmond, California, 3 in the Pacific Northwest along the Columbia and Willamette Rivers. He implemented assembly line techniques adapted from automotive manufacturing. He divided ship construction into discrete stages performed at separate facilities. He used massive overhead cranes to lift prefabricated sections weighing 250 tons. He trained workers on specific tasks, rather than requiring years of apprenticeship. He hired anyone willing to work: men, women, African Americans, elderly workers, people with disabilities. The only criterion was ability to do the job. The workforce at Kaiser's Richmond shipyards exploded from zero in December 1940 to 20,000 by June 1943. By February 1943, women comprised 19.4% of all welders at Richmond. They were called Winnie the Welders, working alongside Rosie the Riveters, though the Liberty ships used almost no rivets. The women worked in the most confined spaces inside the hull: tight compartments, cramped double bottoms, areas where larger men couldn't maneuver, the most critical welds, the below waterline hull sections where leaks would sink the ship. They learned to weld in training programs lasting 2 to 6 weeks: former housewives, former waitresses, former secretaries. They learned to strike an arc, control a bead, read a blueprint, understand metallurgy in the most basic terms. Hot metal fuses, cold metal doesn't. Keep your arc length consistent, watch your travel speed, achieve full penetration. No undercut, no porosity. The welds had to be perfect because men's lives depended on them, and the welds were perfect. Not perfect by peacetime commercial standards where inspectors could reject work for purely aesthetic reasons, but perfect enough for wartime service. The joints held, the hulls didn't leak, the ships sailed. From 1941 through 1945, American shipyards built 2,710 Liberty ships, 18 different yards, but Kaiser's operations alone produced roughly 1,000 ships, accounting for about 37% of total Liberty ship production. The average construction time dropped from 355 days in early 1941 to 42 days by 1944. Kaiser's Richmond Yard No. 2 built the SS Robert E. Peary in 4 days, 15.5 hours in November 1942. Keel laid Sunday morning, November 8th. Ship launched Thursday afternoon, November 12th. The construction was a propaganda victory, demonstrating that America could build ships faster than U-boats could sink them. It was also a genuine industrial miracle. 250,000 parts, 14 million pounds, 75 miles of welding, 4.5 days. The Peary deployed immediately to the Pacific. She served throughout the war, making multiple runs to Australia, New Caledonia, Guadalcanal. She survived Japanese air attacks, survived submarine encounters, survived typhoons in the Western Pacific. The rapid construction didn't make her fragile. She was as tough as any Liberty ship, and tougher than some that had taken months to build. Speed didn't compromise quality. The Kaiser system worked. But some ships were breaking, not many. Out of 2,710 Liberty ships, approximately 1,200 experienced significant cracking during the war, roughly 30%. Most cracks were superficial, deck fractures that could be repaired by welding crack-arresting plates. A few were catastrophic. 3 ships split completely in half and sank. 19 ships suffered Class 1 structural damage that endangered the vessel. For a crash program building 3 ships every 2 days using revolutionary construction techniques, the failure rate wasn't surprising. It was actually remarkably low, except nobody knew why some ships fractured while others didn't. The failures seemed random. Ships built at the same yard using the same materials and the same workers. Some served for years without problems. Others cracked within months. The fractures occurred without warning. No gradual deformation, no visible signs of impending failure. One moment, the ship was intact. The next moment, a crack 600 feet long had propagated through the hull at speeds approaching the speed of sound in steel. The Coast Guard established a board of investigation. Engineers from the Maritime Commission examined failed ships. Metallurgists from the National Bureau of Standards analyzed steel samples. Welding experts studied the fracture surfaces. Everyone had theories: bad welds, inadequate inspection, improper welding procedures, hydrogen embrittlement from welding in damp conditions, residual stresses from rapid cooling, stress concentrations at square hatch corners. Every theory had some supporting evidence. None explained the pattern of failures. What made the Liberty ship failures terrifying wasn't just that ships were breaking, it was where they were breaking and when. The North Atlantic, in winter, the most dangerous waters on Earth, convoys of 50, merchant ships steaming from New York to Liverpool through seas, where German U-boats hunted in wolf packs of 20 or 30 submarines, coordinated by radio from headquarters in France. March 19, 43. Convoy HX-229. 40 merchant ships carrying 500,000 tons of war supplies, aircraft, tanks, ammunition, food, fuel, everything Britain needed to continue fighting. The convoy encountered Wolfpack Raubgraf, 21 U-boats spread across 200 miles of ocean. The battle lasted 5 days. The Germans sank 13 ships. 6 of them were Liberty ships. SS William C. Gorgas torpedoed just after midnight, March 11th. 8,000 tons of cargo, including 900 tons of TNT. The explosion when she sank damaged the U-boat that had torpedoed her. The crew of the Gorgas abandoned ship in lifeboats, 70 men in 3 boats, temperatures near freezing, seas running 20 feet. They watched their ship go down, then waited for rescue. Of the 70 men who reached the lifeboats alive, only 12 survived to be picked up by escorts the next day. 58 died of exposure in the North Atlantic in less than 24 hours. The cold killed them faster than torpedoes. That same month, March 1943, the SS Schenectady cracked in half in Portland. The SS SO Manhattan split entering New York Harbor. At least 20 other ships experienced significant hull fractures. Something was catastrophically wrong. The Maritime Commission faced an impossible problem. Stop building Liberty ships and lose the Battle of the Atlantic. Continue building Liberty ships and risk catastrophic failures that could cost thousands of lives. They chose to continue building. There was no alternative. Britain was surviving on supplies delivered by Liberty ships. The Soviet Union was receiving tanks and aircraft and ammunition through the Persian Gulf and Murmansk on Liberty ships. The Pacific Island hopping campaign required cargo, a capacity that only Liberty ships could provide. The entire Allied strategy depended on maintaining the flow of supplies across the world's oceans. If the Liberty ship program stopped, the war effort collapsed, but the ships kept cracking. SS John P. Gaines in November 1943. Steaming from Dutch Harbour toward Seattle with a cargo of military equipment, air temperature near 0 degrees Celsius. Heavy seas washing over the bow. A crack appeared at the corner of number 3 cargo hatch. Within seconds, the crack propagated down both sides of the hull. The ship folded. The bow section sank immediately. The stern drifted for hours before running aground in Alaska. 10 men died in the bow section. The other 33 survived in the stern. The survivors reported hearing a sound like a gunshot. Then the ship lurched violently. When they came on deck, the bow was gone. Just gone. Severed cleanly as if cut by a giant saw, the fracture surface was flat and crystalline, brittle fracture. The steel had failed without any plastic deformation, without any warning signs, without any ability to redistribute stress. It had simply snapped. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Engineers examining the wreckage found that the crack had originated at the square corner of a cargo hatch. That corner acted as a stress concentrator. Under normal conditions, the steel's ductility would have absorbed the stress. The material would have deformed slightly, spreading the load across a larger area. But something had changed the steel's properties. Something had made it brittle. The U-boats didn't care why the ships were cracking. They just kept hunting. By mid-1943, Admiral Karl Dönitz commanded over 400 U-boats. He deployed them in wolf packs that could overwhelm any convoy escort group. The tactics were brutally effective. Shadow, the convoy beyond visual range. Report its position by radio. Coordinate the attack. Surface at night when radar was less effective. Use superior surface speed to get ahead of the convoy. Dive. Wait. Fire torpedoes at close range. Reload. Fire again. In the first 3 months of 1943, U-boats sank 95 Allied merchant ships in the North Atlantic, over 500,000 tons of shipping, faster than American and British shipyards combined could replace them. The Germans called it the happy time. Dönitz believed the U-boats were winning, that Britain would be starved into surrender within months, that the mathematical tonnage war would decide the outcome before American industrial production could tip the balance. He was wrong, but only barely. The Allies were producing Liberty ships just fast enough to offset U-boat sinkings. 3 ships launched every 2 days, 11 ships sunk every week by U-boats. The margin was razor-thin. Lose 1 major shipyard to bombing. Experience a spike in catastrophic hull failures. Suffer a few disastrous convoy battles. Any of those could swing the balance toward Germany, and the ships kept cracking. The pattern was becoming clearer, even if nobody understood the mechanism. The failures occurred almost exclusively in cold weather, winter and spring in the North Atlantic. The Aleutians, Murmansk convoys, ships operating in water temperatures below 10 degrees Celsius and air temperatures near or below freezing. The same ships that sailed safely through the Caribbean or the South Pacific would crack in the Arctic. The second pattern was structural. Most fractures originated at stress concentrations, square hatch corners, deck cutouts, the ends of welded seams, points where the geometry created locally higher stress. Again, this shouldn't have mattered. Steel's ductility should have prevented brittle fracture at these stress concentrations. The material should have yielded plastically before cracking. Something was preventing normal ductile behavior. The third pattern involved the welds, not because the welds themselves were faulty, but because the all-welded construction allowed cracks to propagate unimpeded. In traditional riveted ships, a crack would reach the edge of a steel plate and stop. The riveted joint between plates acted as a crack arrestor. The crack couldn't jump the gap. But in welded ships, the hull was essentially one continuous piece of steel. A crack could run from bow to stern without encountering any barriers. Maritime Commission engineers developed temporary solutions. They installed crack-arresting riveted seams running the length of the hull, 4 longitudinal riveted joints that would stop cracks from propagating the full length of the ship. They redesigned the hatch corners, rounding them off to eliminate the stress concentration. They added gunwale bars, reinforced deck strakes, anything that might slow or stop crack propagation. The retrofits worked. No ship that received the full suite of anti-fracture modifications ever experienced catastrophic failure. But installing the modifications took time. Thousands of ships were already in service without them. The shipyards were building new ships faster than the Navy could retrofit old ones, and none of the modifications addressed the fundamental question. Why were some ships cracking while others weren't? In England, a metallurgist named Constance Tipper was asking the same question. 69 years old in 1943, Cambridge University Engineering Department, one of the world's leading experts on metal crystallography and fracture. The British Admiralty asked her to investigate the Liberty ship failures, gave her steel samples from failed ships, asked her to determine the cause. Tipper approached the problem systematically. She obtained steel samples from multiple failed Liberty ships. She performed tensile tests at various temperatures. She conducted Charpy impact tests, measuring the energy required to fracture notched samples at different temperatures. She examined the fracture surfaces under microscopes, studying the crystalline structure of the failed material. What she discovered was fundamental. At room temperature, the Liberty ship steel was ductile. It deformed plastically before fracturing. It absorbed significant energy during failure. The fracture surface showed the fibrous, irregular texture characteristic of ductile failure. But as the temperature decreased, something changed. Below approximately 40 degrees Fahrenheit, the steel became brittle. It fractured with minimal plastic deformation. It absorbed much less energy. The fracture surface became flat and crystalline. The steel was experiencing a ductile to brittle transition. Above the transition temperature, the material behaved as expected. Strong, tough, ductile. Below the transition temperature, the same material became brittle. Cracks propagated at high speed. Concentrations that would normally cause local yielding instead initiated catastrophic fracture. The transition wasn't gradual. It was sharp. A temperature range of just 10 or 20 degrees determined whether the ship would survive or break apart. Tipper published her findings in 1945. She developed what became known as the Tipper test, a standardized method for determining the ductile to brittle transition temperature of steel. She demonstrated that the Liberty ship steel had a transition temperature around 40 degrees Fahrenheit. Ships operating in the North Atlantic in winter, where water temperatures hovered around 35 to 40 degrees and air temperatures often dropped below freezing, were operating below the transition temperature. The steel wasn't ductile anymore, it was brittle. The problem wasn't the welding. Martha Reynolds and thousands of other women welders had done their jobs correctly. The welds themselves were sound. The problem was the material selection. The steel chosen for Liberty ships was adequate for riveted construction, where cracks couldn't propagate between plates. It was inadequate for all welded construction in cold water. The chemistry was wrong. Too much carbon, too little manganese. The metallurgy produced steel with a transition temperature that was too high for North Atlantic service. By the time Tipper published her findings, the war was nearly over. The Maritime Commission had already modified the Liberty ship design. Rounded hatch corners, crack-arresting seams, better steel chemistry in later ships, improved welding procedures, better quality control. The incidence of catastrophic failures dropped dramatically in 1944 and 45, but the knowledge came too late to prevent the earlier failures. Too late for the John P. Gaines. Too late for the men who died when their ships broke apart in the Arctic. The Liberty ships won the Battle of the Atlantic anyway, not through superior individual performance, but through sheer numbers. German U-boats sank approximately 200 Liberty ships during the war. Out of 2,700, 10 built, a loss rate of about 7%. The shipyards were building ships 10 times faster than U-boats could sink them. By mid-1943, American production of cargo ships exceeded U-boat sinkings by such a margin that Donitz could no longer achieve favorable exchange rates. The mathematics were brutal and simple. A Liberty ship cost roughly $2 million and required 500,000 man-hours to build. A Type 7 U-boat cost about $2 million and required 300,000 man-hours, but each U-boat could sink perhaps 10 or 15 merchant ships during its service life before being sunk itself. The exchange ratio favored the Allies. Build 3 ships for every one sunk. Build 5 ships for every one sunk. Build 10 ships. Eventually, the U-boats would lose through attrition. In May 1943, the tide turned decisively. Convoys ONS-5 and SC-130 routed wolf packs that had seemed unstoppable months earlier. Allied aircraft with extended range could now patrol the entire North Atlantic, eliminating the mid-ocean air gap where U-boats had operated with impunity. Improved radar, better depth charges, escort carriers providing air cover for convoys, and most importantly, sufficient cargo capacity that losing 13 ships in a convoy battle didn't cripple the war effort, because 30 more ships were being launched that week. Admiral Donitz withdrew the U-boats from the North Atlantic convoy routes on May 23, 1943. The decision marked the effective end of the Battle of the Atlantic. U-boats would continue attacking Allied shipping for the rest of the war, but they never again threatened to cut Britain's supply lines. The tonnage war was over. The Allies had won. Liberty ships had won. Martha Reynolds never knew that. The Schenectady's failure wasn't her fault. She died in 1989 in Spokane. Her obituary mentioned that she had worked in a wartime factory. It didn't mention shipbuilding, didn't mention welding. She had carried the shame for 46 years. The unspoken belief that something she had done, some weld she had made, had caused that catastrophic failure. She was wrong, but she never learned the truth. Constance Tipper continued her research for decades after the war. She became the first female full-time faculty member in Cambridge University's engineering department in 1949. She consulted on submarine construction, bridge design, nuclear power plant safety, any application where brittle fracture posed a risk. Her work on the ductile to brittle transition temperature became fundamental to materials engineering. Every pressure vessel, every cryogenic tank, every structure operating at low temperatures. Engineers now understood that material properties change with temperature and designed accordingly. The Liberty ship program transformed American shipbuilding permanently. The modular construction techniques, the assembly line methods, the use of prefabrication, the emphasis on speed and efficiency over traditional craftsmanship. These approaches continued after the war. The same shipyards that built Liberty ships built the post-war merchant fleet. The same welders who learned their trade building warships built commercial vessels. The industrial capacity that won the war became the foundation for post-war economic expansion. Henry Kaiser's Richmond shipyards closed in 1945. The workforce of 20,000 dispersed. Most of the women welders returned to traditional women's work. Some stayed in industrial jobs. Some used their wartime wages to start businesses or attend college. The GI Bill didn't cover civilian war workers, but some shipyard workers saved enough money to change their lives permanently. They had proved they could do demanding technical work. That experience shaped a generation. 2 Liberty ships survive in operational condition today. The SS Jeremiah O'Brien, berthed in San Francisco. The SS John W. Brown in Baltimore. Both are museum ships. Both still operate under their own power. The John W. Brown was built in 42 days in September 1942. She made 13 voyages during the war, survived the D-Day invasion, where she delivered cargo to Omaha Beach. She outlasted the war, outlasted peace, outlasted decades of merchant service. In 1988, volunteers began restoring her. Today, she's a floating reminder that rushed wartime construction, when done with proper materials and proper technique, can produce vessels that last 80 years. The third surviving Liberty ship, the SS Arthur M. Huddle, is a non-operational museum ship in Greece. She served in the American merchant fleet until 1967, then sailed under Greek flag until being retired. 3 ships out of 2,710. The rest were scrapped, sold for scrap metal that went into building the post-war world. The steel that carried Liberty to Europe went into building cars and bridges and skyscrapers. The cycle completed. The story of the Liberty ships is the story of how wars are actually won, not through brilliant strategy alone, not through heroic combat alone, through industrial production, through logistics, through the grinding, unsexy work of building enough ships fast enough that losing 200 doesn't matter because you built 2,700. Through welders like Martha Reynolds who did their jobs correctly even though they would never receive credit. Through engineers who solved problems without understanding the underlying science. Through workers who built ships while their sons and brothers sailed on them. It's also the story of failure. Of ships that broke apart because nobody understood that steel becomes brittle when cold. Of men who died because the science of fracture mechanics didn't exist yet. Of women who carried unearned shame because investigators needed someone to blame. Of the gap between engineering ambition and metallurgical understanding, of the cost of learning. Constance Tipper's research prevented future failures. Modern ships don't crack in half in cold water, because engineers now specify steel with appropriate ductile to brittle transition temperatures. Pressure vessels don't shatter because materials are tested at their service temperatures. The science that emerged from Liberty ship failures has saved countless lives, but that knowledge came too late for the 78 men who died when their Liberty ships broke apart at sea. The final count, 2,710 Liberty ships built between 1941 and 1945. Approximately 200 sunk by enemy action, about 7%. 1,200 experienced significant cracking, about 44%. 19. Suffered Class 1 structural failures. 3 broke completely in half. 1, the Schenectady, fractured at the dock before ever entering service. The program was simultaneously a catastrophic failure of material science and the most successful emergency shipbuilding program in history. The U-boats sank ships. The North Atlantic cold broke ships, but American industry built ships faster than they could be destroyed. 3 ships every 2 days, 11 million tons of merchant shipping launched in 1943 alone. The mathematics overwhelmed the enemy. Quantity became its own quality. The Liberty ships weren't elegant, weren't fast, weren't particularly seaworthy. President Roosevelt called them ugly ducklings. But they carried 10 million tons of cargo. They transported 2 million troops. They delivered the material that won the war. And they were built by welders who learned their trade in 6 weeks. By women who left housework to work in shipyards. By workers who understood that their welds would carry their brothers and sons across oceans where submarines hunted in wolf packs. They took pride in their work, even though the work was temporary, even though they knew they'd lose their jobs when the men came home, even though newspapers would later blame them for failures that weren't their fault. Martha Reynolds made perfect welds on the Schenectady. Every single one. The metallurgists who examined the fractures confirmed it decades later. The cracks propagated through the steel plate, not through the welds. The welding wasn't the problem, but Martha never knew that. She carried the weight of that failure until she died, and she was one of thousands who carried similar burdens. The cost of wartime production wasn't just measured in dollars or man-hours. It was measured in shame carried by people who had done nothing wrong. The Liberty ship program succeeded despite catastrophic failures because the failures happened at a scale the program could absorb. Lose 3 ships to structural failure. Build 2,700 more. Lose 200 to U-boats. Build 2,500 more. The program worked because American industrial capacity could outlast German submarines and survive its own mistakes. That capacity emerged from workers willing to learn new trades, from industrialists willing to try revolutionary techniques, from a society that could mobilize millions of people toward a common goal. It's a story about welding, about steel, about ships, but fundamentally, it's about the people who built those ships under impossible conditions, who carried the weight of that responsibility, who succeeded despite failures, who won the tonnage war through sheer persistence. The mechanic who modified control cables on P-38s saved pilots through unauthorized field modifications. The boat builder who added a ramp saved soldiers through practical innovation. The welders who built Liberty ships saved civilization through mass production. Different stories. Wars are won by people who solve problems, even when the solutions are imperfect, even when the cost is high, even when history doesn't remember their names. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.